So in this video, we will be looking at intermolecular forces and then going into solids and liquids. So first thing we want to do is kind of look at what intermolecular forces are. So intermolecular forces are those attractive forces that exist between molecules. So intermolecular means between two or more molecules. If you contrast this to intramolecular forces, these are attractive forces. Think about the bonding that we did in Unit 3 that hold atoms together within a single molecule. So all of Unit 3 was about bonding, intramolecular. What we're talking about now is intermolecular. So what's happening between molecules. In general, you're looking at intramolecular forces are stronger than intermolecular forces. And that kind of makes sense. When you put water on the stove to boil and you heat it up, that heat is going into breaking the intermolecular forces holding the particles together as a liquid as opposed to it being a gas. You're not breaking up the intramolecular forces and splitting the H2O into H2 and O2. That would be changing the bonds. Here, you're changing those interactions between molecules. That's intermolecular. There's four main types of intermolecular forces, and I've labeled these from strongest to weakest. The first are the Coulombic forces. This is what happens between ions. You get a very strong interaction between full positive ions and full negative charges. That's a very, very strong interaction. Because that's so strong, that's what explains the high melting point and boiling point of these ionic compounds, because all of the individual pieces are held together by this strong force. In order to, liquefy a solid or vaporize a liquid to a gas, you have to disrupt those intermolecular forces. If those forces are very strong, it takes a lot of energy in order to disrupt them. That's why ionic compounds, something like table salt, you're looking at the melting point being many hundreds of degrees Celsius. The boiling point even higher, because you have to disrupt all of those very, very strong intermolecular forces. I'm going to skip the second one, hydrogen bonding, just for a second, because it's really a special case of the third, which is dipole-dipole. In dipole-dipole, you're looking at things that have dipole moments, polar molecules. When you're looking at a polar molecule, what you're really looking at is, as you know, a polar molecule has a positive end and a negative end. And what ends up happening in an intermolecular manner is that the partial positive from one molecule is attracted to the partial negative end of another molecule. So positives and negatives are still attracted to each other between molecules. It's just these are much weaker than Coulombic forces. Coulombic forces, we have full ions. Here for dipole-dipole, we have very, very, very small charge buildups that are happening, but it's still a positive versus a negative. Now that we understand dipole-dipole for our polar compounds, we can go to the second one, which is hydrogen bonding. This is probably the worst termed thing in all of chemistry. And it's the worst termed thing in all of chemistry because it's almost intentionally misleading. When we say bonding, we often talk about intramolecular. How are the atoms within a molecule held together? That's not what this means. What hydrogen bonding really is hydrogen bonding is not a bond at all. What it is it's a special type of dipole-dipole interaction. It's a strong dipole-dipole. It's so strong, it gets its own category. To get this special type of dipole-dipole, you have to have a certain specific structural feature in the molecule. And that structural feature is that hydrogen needs to be directly bonded to either nitrogen, oxygen, or fluorine. Those three are our most electronegative elements. So that's going to set up a very strong dipole-dipole that has some special properties to it, so we give it its own category. Remember, it's not enough just for hydrogen to be in the molecule with nitrogen, oxygen, and fluorine. It has to be directly attached to develop this very, very strong dipole interaction. The fourth type goes by a lot of different names. These are sometimes called dispersion forces, sometimes called London forces, sometimes they're called London dispersion forces, sometimes they're called van der Waals forces. This is the idea of an induced dipole moment. Now, we need to explain really what that is. For these dispersion forces, all molecules have dispersion forces. But there's one type of compound that we haven't talked about yet, and those are the nonpolar compounds. Nonpolar compounds will only have these dispersion forces. So when we think about these nonpolar compounds, there's got to be something holding them together as liquids and as solids, and that's the idea of an induced dipole moment. And the larger the molecule is, the more these dispersion forces are present. All compounds have dispersion forces. Even if you have one of the other types, you will still also have these dispersion forces as well. And the way to think about this induced dipole moment is even if you have a nonpolar compound, the electrons in there are going to be randomly distributed. But when they're randomly distributed, they're not stationary, they're moving about. So what can happen is, just based upon the random nature of the electrons, there may be one specific small snapshot in time where they're not completely evenly distributed. If they're not completely evenly distributed, well, then you're still going to get the smallest amount of partial positive and partial negative charge buildup. Much, 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 much smaller than we saw in dipole-dipole, and not permanent. This is temporary. But just that temporary, super small polarity that can exist, even for a fleeting moment, is enough to induce that in a neighboring molecule. So you still have potentially some pluses and minuses happening, just on a super, super small scale. That's just caused by the random nature, the random flux of the electrons. So we kind of order these from strongest to weakest. So you should be able to look at a molecule and say, what type of intermolecular forces does it have? The stronger the intermolecular forces, the higher things like melting point and boiling points are ended up going to be. Those that have weaker intermolecular forces will have lower melting points and boiling points. This idea of the types of intermolecular forces kind of is a recurring theme that happens throughout this entire section. So we're going to be talking a lot about those intermolecular forces. We spent a whole chapter talking about gases. We should spend just a little bit of time talking about liquids. And a lot of terms here. First term we want to talk about is the idea of surface tension. So when we're talking about surface tension, what we're dealing with is the amount of energy required to stretch or increase the surface area of a liquid by a unit area. So almost think about if you could go down, and if you've ever folded a big tarp or a big square tablecloth or anything, almost imagine a big square piece of fabric that everyone's pulling on each side. They're trying to stretch that across. That's the idea of surface tension. Same thing happens from liquid. High surface tension comes from strong intermolecular forces. In order for an object to enter into a liquid, it has to break the surface tension. You have a little bit of experience with this. If you've ever belly flopped into a pool or went off the high dive, you know that water is kind of hard. it's not exactly soft. And I'm not talking about whether you have ions in it or use a water softener. That's what I'm talking. That's not what I'm talking about. I'm talking about physically hard. It stings when you do a belly flop in the pool from a high distance. That's because in order for your body to enter that water, it's got to disrupt those intermolecular forces, that surface tension that's forming the surface of that liquid. Some other terms we want to talk about are cohesion and adhesion. So cohesion is the intermolecular attraction between the like or same or similar molecules. Adhesion is that intermolecular attraction between unlike or dissimilar molecules. And it's the interplay of these that give you some of the different properties you associate with liquids. It's the combination of these properties. So I'll do an example of that. You've been in lab, you've poured water into a graduated cylinder. And if it's a small enough diameter, one of the 10 milliliter ones, what you've noticed is water in the test tube doesn't lay flat. It's curved. There's a meniscus. So on the left, I have a test tube filled with water, and you see kind of the smiley face meniscus. Why are you getting that smiley face meniscus? You're getting that smiley face meniscus is because for water and the glass or the plastic on the sides, the adhesion is greater than the cohesion. Water would rather stick to the sides of the container than stick to itself. Water is different than the glass or the plastics. That means the adhesion is greater. Not all liquids behave that way. We don't use mercury very much, but if you've ever looked very closely at a mercury thermometer, you've noticed that the meniscus for mercury faces the opposite way. You kind of get the frowny face meniscus. It's bulged up. In this case, what you're seeing is that cohesion is greater than adhesion. Mercury would rather interact with itself than interact with the walls of the container, the sides of that container. That's one of the reasons why mercury is not used as often as it used to be. One, it's kind of toxic. Two, it's a complete disaster to try to clean up after it. If you've ever broken anything with mercury, what happens is mercury will then form tiny little balls. Think about a sphere that maximizes contact with itself and minimizes contact with the outside, and then rolls around everywhere. So it's really tough to clean up because it just goes and goes everywhere. Another property we want to be familiar with for our liquids is the idea of viscosity. Viscosity is a measure of a fluid's resistance to flow. The greater the viscosity, the more slowly that liquid flows. Stronger intermolecular forces results in a higher viscosity. Viscosity decreases as temperature increases, and you have some experience with this. If you've ever dealt with melted chocolate, you know that when you get chocolate very, very hot and it's melted, it starts to get very thin and very runny. That's a lower viscosity. Even when it's still hot, but it's cooled down some, it kind of get a little bit thicker. It doesn't flow as easily. You can see that as temperature increases, viscosity decreases. It's easier for it to flow. You also have some experience with this with your car engine. You know, when it's really, really cold out, you're often told to warm up your car before you really drive it, before you really put some stress on it. Well, that's because when it's really, really cold out, the oil doesn't flow as well. You don't want to stress the car driving it before it's really had a chance to circulate properly through the engine. While we're talking about liquids, we have to spend a little bit of time talking about water, our most important liquid. So water is a truly remarkable liquid. It's very, very different than a lot of other substances that are liquids or things that you would think might be similar to water. Water is a very good solvent for many compounds, especially ionic compounds. We really make use of that when you think about all the different ions that can dissolve in water, many of which are necessary for life. One of the things that you'll talk a little bit about next semester is the idea of specific heat, but I just want to introduce it here. Specific heat, water has a very high specific heat. And what a high specific heat means is the ability to absorb and give off a large amount of heat without a large change in temperature. What that means is water heats up and cools down very slowly because there has to be a lot of heat exchange before you see a change in temperature. And you're already very familiar with this. When you put a pot of water on the stove to boil, it takes forever. It takes a long, long time to get it to boil. The reason why? You have to give it a lot of heat because of that high specific heat of water. If you make ice cubes the old-fashioned way, you've also seen that. Pouring water into one of those plastic ice cube trays and then throwing it in the freezer. Well, that takes a long time as well because in order to freeze that water, it has to give off a lot of heat. It takes a long time. Water has a very high specific heat. It changes temperature very slowly. You compare that to something with a low specific heat. So things with low specific heats are things like metals. Metals heat up very quickly and cool down very quickly. You have some experience with this. Think about on a hot, sunny summer day. You just get into your car. What's that hottest piece of the car? That metal seat buckle for your seat belt. That's really, really hot. Or you might have some experience with this on a cold day in the winter if you've ever parked very far away from where you're at, like at a sporting event or a concert or the mall, where you're way out, very far away from the building, takes a 10 or 15-minute walk to get to your car. Well, even though your pocket's warm and your body's warm, by the time you fish your keys out of your pocket, those keys are cold because they've changed temperature quickly. This high specific heat of water explains a lot of your local weather patterns. We think about it in the summer. In the summer, it's a lot cooler near the shore than it is inland. That's why everyone's going to the shore in the summer, kind of cool down. Well, we want to think about why that is. If we think about a hot, sunny August day, the air temperature might be 95. But what will the water temperature be? It's not going to be 95. It's probably going to still be in the upper 60s maybe. It's a lot cooler than the air temperature. As a result, it's going to suck in heat from the surrounding air and give us a cooling effect. Similar process happens in the winter. In the winter, when you're near the shore, it's much warmer than it is inland. Now, don't think about wind chill. We're talking the actual temperature, and you're familiar with this. It's warmer near the shore in the winter than it is inland. Well, that's due to the high specific heat of that ocean water as well. You're getting snow inland, it's warmer near the shore, you're getting rain. Well, why is that? Because it's just warmer near the shore. On a January day, the air temperature may be 20 degrees. The water temperature though is probably still in the 40s. That's a lot warmer than the air. So that heat from the water is going into the air and giving you a localized warming. You don't see the big temperature swings in water that you would in air because of that high specific heat. Another interesting feature is ice is less dense than liquid water. Maybe thinking about this and saying, so what? Well, this is true for very, very, very few compounds. Almost any other compound you think of, the solid phase is more dense than the liquid phase. For water, it's the opposite. And it's kind of important that it's opposite. It's really important for kind of how life developed, especially life kind of on land, out of the oceans? Well, we know how important water is. Let's kind of imagine this a different way. Let's imagine what would happen is if ice was more dense than liquid water. Well, on a lake, a pond, a stream, or a river in the winter, what would happen is you would start forming ice on the surface, and then that ice being more dense than liquid water would sink to the bottom. Then you'd form more ice on the surface. That would sink to the bottom, and more and more and more. And what would end up happening is you would completely freeze that lake, pond, river, stream from bottom to top, because that heavier ice would sink to the bottom. But that's not what happens. Ice is less dense than liquid water. So what ends up happening is you form a little bit of ice on the surface. Well, it stays there because ice is less dense than liquid water. What that ice then does is that's shielding the rest of the liquid water underneath from that very cold air temperature. That's going to keep, if it's a deep enough lake, pond, or river and it isn't super cold, you're only going to get ice a couple inches thick, a couple feet thick. You're still able to have liquid water underneath, which is very important for the aquatic life. So although it doesn't seem like a big deal when we just think about ice sitting in our glass of water or lemonade, it's a very key thing for kind of how life can exist. All these properties that we talk about for water are the result of the hydrogen bonding in water. It's a very specific three-dimensional network that gives water a lot of these very interesting and unique properties. Talk real quickly just about some solids. And we have two types of solids, amorphous solids and crystalline solids. And amorphous solids lack a regular three-dimensional arrangement of the atoms or the molecules. In a crystalline solid, you have a regular repeating pattern. An example of a crystalline solid would be something like diamond or a salt crystal. An example of an amorphous solid would be something like glass. When you think about glass and amorphous solids, they're almost like super thick liquids that don't flow that much, but they actually can flow a little bit. When you think about a very, very old building, many hundreds of years old, that has an original piece of glass in there, what you might be able to see is that it's a little thicker at the bottom than at the top. Well, that's because glass is really almost like a super, 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 super thick liquid with that kind of random arrangement of the atoms, such that over a long amount of time, there's actually a little bit of flow. You would not see that flow in a crystalline solid like a diamond or a salt crystal, because there you have a regular repeating pattern. There's nowhere for those atoms or those molecules to fall down into. So we've talked about solids, liquids, and gases. We want to talk a little bit about going between all of those different phases. We want to talk about some actual phase changes here. So I drew a kind of phase change diagram. And this phase change diagram kind of looks at what would be happening if you took a solid that started very, very cold and slowly exposed it to a heat source, a gradual heat source. What would happen over time? So I kind of drew this out. On the vertical axis is the temperature. On the horizontal axis is time. So we're starting kind of right at the origin here. And what you're seeing is as we're supplying heat, so all this region before point A, as we're supplying heat, what's happening is the temperature of the solid is increasing. It's going from very, very cold to kind of cold to less cold. Eventually, though, we're going to supply enough heat to start melting that solid. And that's what you see between points A and points B. Between points A and points B, what you see is you have solid and liquid in equilibrium. This would be melting or freezing. And what you really want to notice about this is flat. There's no temperature change happening here. And the reason there's no temperature change is even though we're still supplying heat, that heat is going into that phase transition. That's not going to have any temperature change. That's why it's flat. Eventually, though, you will melt all of that solid. And that's what you see between regions B and C. Once you've melted all of that solid, now you have all liquid. As you continuously supply heat to this, what's going to happen? Temperature of that liquid is going to increase. That's what you see between points B and point C. Eventually, you're going to get to the boiling point of that liquid. That liquid is going to start to form into a gas. That's what you see between point C and points D. The liquid and the gas are at equilibrium with each other. That would be boiling or condensing if you're going the other way. Note again, there's no temperature change. This is a flat region of the curve. That's because the energy that we're still supplying to this is going to disrupting those intermolecular forces to change things from a liquid to a solid. Eventually, as you're still supplying heat to this, you will turn all of the liquid to a gas. If you keep supplying heat to that, that's what's happening after point D. The temperature of the gas is going to increase, just what we would have expected here. So key things about this is when you are at a phase change. So when you are at a phase change, here, here, when you're at these phase changes, we're at a flat region on the curve. That means there's no temperature changes happening. That's really important to kind of remember when you're transitioning from liquid to solid or solid to liquid, liquid to gas or gas to liquid. You're not seeing a temperature change as a result of that. What we also want to talk about is a phase diagram. In a phase diagram, what this is this is a description of the temperature and pressure conditions at which a substance can exist as a solid, a liquid, or a gas. And I drew a very generic one here. And what this really represents is hundreds, if not thousands, of data points, basically taking a compound, exposing it to different combinations of pressure and temperature, and recording what phase is it in at that specific temperature and pressure, solid, liquid, gas. And then instead of leaving that in table form, it's kind of making a pictogram out of this. So there's some key things that we're looking at here. One of the key things is something called a triple point. The triple point is a set of conditions at which all three phases are in equilibrium with each other. That's kind of where all of these hit. If I kind of circle that in here, you can see that's the spot where they all hit. If you were at that exact temperature and pressure for a compound, what you would end up seeing is you would end up seeing all three, solid, liquid, and gas, in complete equilibrium with each other. They would just continuously be transforming into each other indefinitely if you had a really closed system for this. We're not usually used to seeing that because what happens is for water, let's say, 1 atmosphere of pressure for water, well, that would kind of be up here where we would go through solid, liquid, and gas as we increase the temperature. Not all compounds will do that. If we looked at kind of a different compound for this, if we looked at something like CO2, carbon dioxide, frozen CO2 is called dry ice. Well, if you've ever messed around with dry ice, you know you don't get liquid. It goes right from a solid to a gas. That's kind of sublimation. Well, that's because in red, what I'm going to draw here is for CO2, 1 atmosphere of pressure, where we're actually handling things at, is way down here, such that as we're increasing the temperature, we get solid, 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 and then we go right to gas. We never hit that liquid part of that. So we also want to talk a little bit more about solutions as well. You know, actually dissolving things into liquid. And we talked a little bit about solutions in Unit 2. We're not going to do any calculations in this unit. We're going to stick to it being very, very qualitative. We're going to talk about some types of solutions, some other classifications that we didn't really get to in Chapter 4. We can classify solutions by concentration, and there's kind of three types. There's saturated, unsaturated, and then a kind of a rare but special supersaturated. So let's talk about each one of these. Saturated contains the maximum amount of a solute that can be dissolved at a given temperature. It's saturated. You could not dissolve any more. No more solute could be dissolved at that point. Unsaturated would be not saturated. This would contain less than the maximum amount of solute. What that means is more solute could end up being dissolved in this. There is a special case, it's called supersaturated. Well, supersaturated contains more solute than a saturated solution. Well, right now you're thinking of saturated as a maximum. How can I be above the maximum? Maximum means maximum, right? Well, maximum that can be indefinitely stable. You can keep a you can keep a saturated solution around indefinitely. There may be small periods of time where you can go over that maximum, and that would be a supersaturated solution. These are very, very unstable. Eventually, the extra solute that made it supersaturated instead of saturated will come out of solution. And sometimes you see this in kind of some of the magic shows or chemistry demonstrations where the person kind of waves their hand over a beaker and all of a sudden the liquid turns into solid. Well, what they had there was a supersaturated solution. And what they did is they dropped a small little piece of lint or something. And just that piece of lint falling on the surface of that solution was enough of a disturbance to get that extra solute out of that solution. So supersaturated, not long-term stable. When we think about solutions, we often use the adage like dissolves like. Do not use this as an answer for a quiz or a test question because it answers nothing. It's just a little subtle mnemonic reminder of what the actual meaning is. And what it means is polar solutes tend to be soluble in polar solvents. Non-polar solutes tend to be soluble in non-polar solvents. That's the like dissolves like part. Things that are similar in polarity tend to dissolve in each other. Things that are not similar in polarity are not going to dissolve in each other. So we're not going to do any calculations for solutions this unit, but just some other concentration units that sometimes get used I at least want you to be familiar with. So some other concentration units. Could be percent by mass. Well, anything by mass is a part compared to a total. So you could talk about the mass of the solute in a solution compared to the entire solution. That'd be a decimal. Change it to a percentage. Molarity we're pretty familiar with. Nothing to say there. Mole fraction. So that's the moles of something, the moles of A divided by all of the moles that are in there, kind of the fraction of what you're interested in compared to all of the things that are in there. Also sometimes molality, kind of related to molarity but a little bit differently. Molality is moles of solute divided by the mass of the solvent in kilograms. And you sometimes see that a little bit more in industrial practices with bigger things when you want to work in bigger units like something like kilograms. Again, no calculations for the solutions here, but just some other concentration units I want you to be familiar with. I'll talk a little bit about the effective temperature on solubility. And for this, it really matters, are you a solid or are you a gas solute? Most solid solutes have an increased solubility as your temperature increases. And this kind of makes sense. You're familiar with this. You can dissolve more sugar in hot water than cold water. And the rationale for that is the more energy you have, the more molecular motion, the easier that those solvent particles will have in dissolving those solute particles. Gases act differently. If your solute's a gas, most gases have a decreased solubility as temperature increases. And you're familiar with this as well. Think about what goes flatter faster. Think about a carbonated beverage. What's going to go flatter faster? If that beverage is warm or cold? Well, now you've thought about it. If it's warm, it will go flatter faster. More of the gas will escape. And the idea for this is what keeps the gas molecules in solution is they need to have enough energy to break the surface of the liquid to escape it. As temperature increases, the gas molecules move faster, allowing more to escape. We kind of look at this, if I just draw a kind of open bottle of a carbonated beverage here, if this is rather cold, what ends up happening is these particles, when they come up to the surface, well, if they're not moving very fast, they're not going to break through that interface and they're going to just stay in the solution. But if they're moving fast, they're able to punch through that solution and escape. Once they've escaped, there's no going back for that. We also have pressure can affect solubility as well. Again, this is only for gases. And what pressure does is the greater the pressure of the gas over the solution, the more of it will dissolve. So here what I drew is I drew a closed container of a carbonated beverage. So here I have gas particles in solution and above, and some of them are going out of solution, some are going in. If I have a lot of pressure above the solution, that's going to force more of it into the solution and I get more carbonation that way. That's why when you open up a carbonated beverage, it's at a pressure more than 1 atmosphere. You hear that release of pressure, whether you open up a can of soda or a bottle of soda or sparkling water, anything that's carbonated, there's more than 1 atmosphere of pressure in there because as a result, you can get more into that solution. So the last couple pages is I just wanted to give you some example questions for trying to use some of the things we talked about with liquids, solids, solutions, intermolecular forces, for you to kind of have a look at and kind of go through these and think about, are you able to answer these type of questions?